Hello, my name is Heber. Today you present about the advanced section 2 about the functions in PhysiCell. All the material of this presentation will be in the repository of the workshop. So for starting, let's list how goals of this presentation. First of all, I introduce the full modeling workflow. Um, I'll give a typical form, syntax, or purpose of the PhysiCell functions. Uh, Learn about the availability of the custom functions and the cell class, and learn how to assign new functions to the cell definitions, and learn how to create add-on functions. So for that, you present two examples. One short example, where basically you show where you need to change the C++ code for change the update phenotype function, and one full model when I will represent the anti-tumor immunity model. So for idea for modeling using PhysiCell and generate a custom C++ code, we will follow this workflow. We basically, for starting, we plan the model, populate the project. Usually we're using the template project as the mainly of the sections here in the workshop. Edit the configure file, the XML, as you already know. Just edit domain, edit macro environment, cell definitions, if necessary, custom variables and custom parameters. Define the rules for your project and populate the cells, initialize with the cell placement. You can use the PhysiStudio for that, or you can code in the setup tissue function. So, but in that presentation, I will focus more in that part of the edit custom models, where you developing code in C++ for generate a new dynamics where it's not possible doing by rules. So for that, I will explore more how include new functions for declared functions like custom.h and implement them in the custom.cpp. Assign the functions to the cell definitions, and eventually I will show how assign function as well for as a add-on in the main.cpp. In our workflow, we building after we did the editing and the custom .cpp and adding the functions, and run and visualize the results using PhysiCell Studio. So for starting in terms of the coding, I will just point out some special functions in the PhysiCell. Let's starting by just the signature of these functions in the custom.h. So basically in custom.h you can define the globals variable here and set up the important functions where default from the PhysiCells is a create cell types, where here you set up all the cell types, adjust the phenotype, adding the custom data from that cells is necessary, and vector. Some of the custom data you can just add in the XML, and assign the function who I will show later. Another function, important function, is the setup functions. That one is I mentioned before. That one, if you not want to create your initial condition by the PhysiCell Studio, you want just a coding your initial condition placement, the cells, you could coding in that function setup issue. The custom functions is basically the function I will talk more about here. Is if you want to change the phenotype functions, the custom the custom function and assign them for some cells, and the contact function the same way if you want to assign for some of them the cells. Another important function is the coloring functions. If you want to change the structure of the SVGs, you can change the coloring function. This will be the subject of the section 3, advanced section 3. So for the main.cpp, I'm just highlight here exactly that mainly functions I mentioned, how you calling, how the PhysiCell calling them by default. So initially they set up the microenvironment for solving the substrate diffusion, and set up the environment for the cells, where they create exactly that signature for the functions and given the structure of the cells by creating the cell types, and the cell initial placement in the domain by the setup tissue. Another function I mentioned is the color function. That function comes here in that region after the setup tissue. You can name the name of the coloring function you have if you are using one come from the PhysiCell by default, or if you want to custom your coloring function. So this special place in the main CPP, this is where you can go with add-ons functions. For example, if you want to change something about the all behaviors of the agent, you can go with here with some function. I will give you one example of that in the full model example. So for the summary of all this stuff I'm talking about, basically the workflow for doing changes in the C++ code, you need to just declare the function in the custom.h, implement these functions on the custom.cpp, assign your custom functions for the cell definition you want in your project in the function create cell types. Declare any cell parameters for the custom functions in the custom data part in the XML file. And if you want as well, include user parameter in the XML file. So let's start by digging into each functions. So basically, the signature of all functions in almost all cell functions in the PhysiCell following this form have one pointer for the cells, the address of the phenotype, and the delta t for evolution of that function. So these functions can access some features of the class cell. This is the state, the custom data, where you can use in the already building functions for setting, getting some special custom data. The cell functions, where you measure more in details of that special functions. The cell phenotype, where you can use in the behaviors of these phenotypes and signal and assess them by get and set functions. The reference phenotype, that one is where you define the XML. You already define some parameters. We consider that parameters as the reference. Some of them is default from the PhysiCell, but you can change it as well in the XML. Another thing is you can access is the neighborhood microenvironment, where you can access the substrate value of this the neighborhood of these cells, the intracellular substrate of these cells, and the gradient of the substrate in each cell. So for the functions, especially the function on the cells, we have a bunch of them. The first one is the volume update. This is one default function where they are updating according to the target volume. They update migration bias. That's by default is null, unless if you enable the chemotaxis. The custom cell rules is that one if you want to change one custom cell rules. The update phenotype, that one is is updating according to the phenotype time step. The update velocity, where they compute all the forces acting in the cells and calculate the velocity. The set orientation for define the mainly directions for when you define the planes for you can define actually the planes for cell division. The contact function initially is null as well in evaluating the mechanics time steps. All of these functions basically evaluating updating according to the mechanics time step, unless the update phenotype have your all time step. So digging into what the purpose of these functions, the volume update function, as I mentioned, they dynamically grow shrinking cells towards the target volume. The update migration bias, that one basically updating according to the persistence time of the migration. They change the direction of the bias. The custom cell rules, that one if you want to customize one special rule in your project, you can go with that rule, that function, and that function updating according to the mechanical time step. The update phenotype, this is basically the more useful function for when you change the behavior of the phenotypes in your project. You can change that function, and that you updating according to the phenotype function as a default is 6 minutes. The default of the mechanics, I forgot to mention, is 0.1 minutes. The update velocity, that one is basically taking out all the functions for determine the equilibrium between the cells, the forces that includes the forces of the migrations, the force of the adhesion, repulsion. If you have as well some elastic attachment. The set orientation, that one, as I mentioned, you define the orientation of the cell division, where by default they randomly select one plane for doing that process of division in 3D. In 2D, usually that plane will be into an XY plane. The contact function, that one you can adding or removing spring links between them. This is evaluate each mechanic step. So one short example, and if you want to change the phenotype function for one specific cells, is basically we need to declare these cells in the custom.h. Describe that function in the custom CPP, right, in the code. In that code, basically here we just giving one example for getting the one custom data named rate, and getting that for that variable rate, it's double variable, and change a cell apoptosis rate by using the set single behavior, and change that behavior according to data rate custom data. So basically, this is one typical example when you want to access some custom data and change some behavior. And this behavior here is the apoptosis. And by last, you need to assign this new function, my phenotype function, for the right cell type. In our case here, this project, we just assign for the cell default, because in this case we have just that cells in the hypothetical scenario. And the assign of this function will be in the create cell types in custom.cpp. So I mentioned here now some handy C++ functions where you can use for develop your project. The first one is a find cell definition. you can use it for that function. You can use in the name of the cell or the type ID of the cells as an integer. Another handy C++ functions is create and place new cells. For the create, have a two kind of the signatures. You can not given the name any argument for that functions that you create one cells as a type default. That means that the type ID is 0, or you can given the definition, the cell definition address for pointer for this cell, and you create exactly that type of the cells. And the function for assign position, when you given one vector of the size 3, when you given the position x, y, and z for assign these new cells. This is just highlighting this assign position. When you're using that, you already include that data from BioFVM as well. Is a solver for the substrates. That is very important for coupling the continuous solution of the differential equation and the ABM dynamics. So another handy C++ function is the part of the drawing random numbers. You can use in a uniform random, the normal random distribution, and you can have someone, or you can drawing from the uniform unit circle or for the uniform unit sphere. That one is useful if you want to, for example, put some cells in a circle or a sphere. You can use these functions. And another handy function is the choose event. That one basically you give a non-vector of the probability, choosing one integer between 0 and minus 1 for giving that probability. This probability that some must sum to 1. So this is important if you want to sample one event from one discrete possibilities of the events. So let's move on for the full model workflow. In this example, I will try to reproduce the sample anti-tumor immunity. In that example, we want to show this cell cycle of the anti-tumor immunity, which is basically starting by the cells, the dead cancer cells releasing the dead antigen, the antigen-present cells, you're taking that antigen and migrating to the, doing the process of the intravasation, migrate for the lymph node, and then the lymph node, you are priming and activating effector T cells. That effector T cells you are extravasating from the blood vessel to the microenvironment and recognize the eventually recognize the cancer cells and kill them. This is the cycle of the anti-tumor immunity. So for that, we are modeling simplistically here. We are just using 3 cells. The cancer cells, we will consider a classical mechanical pressure, decrease the cell cycle entry. The dead cells release debris. We consider the antigen presenting cells. That antigen present cells, you chemotaxis store the debris, update the debris, doing the process of the activation when in contact with the cancer cells by increasing the cell cycle entry and release pro-inflammatory factor. And after activating, some of them you migrate to the lymph node for doing the process of the activation. We are modeling as well the effector T cells. That effector T cells you can from the response from that APC's migration to the lymph node. that T cells will migrate from the lymph node and extravasate in microenvironment. Then you have a chemotaxis storage the pro-inflammatory factor, update pro-inflammatory factor, and attack cancer cells. So for following up this model for that example, you can download that project and extract that project and use in project folder by just giving the command load and load the project anti-tumor immunity, and after that you make for building. After building, you can open the PhysiCell Studio for interact with the code and run it and visualize the results. So let's begin in some. I just highlight some parts of this full model here, where I using this mainly I use the C++ part for coding. Phenotype function for APCs. So initially, just we create one phenotype function for the APCs specifically because we want to modeling. I forgot to mention, but exactly that part highlights here for the migration to the lymph node, the intravasation, and migration from the lymph node of the effector T cells. You be necessary doing extra work in the C++ because all of those rules could be done by rules, as you saw much of them in the previous sections. Okay, let's go. Let's return. Okay. By writing that functions for updating phenotype for the APCs, we just started by our workflow. We declare that function in custom.h, write the function in custom.cpp, getting the intravasation rate, increment the intravasation count. That needs to be thread safe because here we are visiting all the cells in parallel. If you counting using that global variable for counting intravasation, you need some kind of to break all the threads and increase this counting, and after that release all these threads for restarting the job. And they remove that cells. That one needs to be thread safe as well. But that one, the PhysiCell already has some capability for handle with that. The capability for doing that is that exactly using that function flag for removal for the PhysiCell. And that one for remove all attachment cells and remove all spring attachments, it will be necessary for kind of the don't interact anymore with another cells. Once a time you remove these cells. Here we're not using attachment cells and spring attachment, but it's here just in case if you want to adding this kind of the capability in the model. This is already you'll be able to handle with this attachment cells and the spring attachments. So, and after that, we assign the function to the cell definitions. We go into in the custom CPP, and in the function create cell types. And there is one part there where it's specifically for you change your custom cell definitions. You can add in these two lines. Basically, in that two lines, the first one, we have the cell definition pointer, where we find that cell definition function for APCs, and we give it to that pointer. And change the functions of the update phenotype of these cells, APCs, naming the new function for phenotype update. This is a APC phenotype function. So another part or another function we create is the lymph node update. That one for represent the process of the getting the intravasated cells and giving for the domain some extravasated cells. So we go into the same workflow, similar workflow actually. We declare the function in custom.h, write the function in CPP. That function have some kind of the special capabilities. First of all, we consider in that function the updating according to phenotype delta t, because the function who has doing the intravasating process follow this phenotype delta t. So we need to make sure they matching with the same time step. Save the numbers of the intravasate cells and the history of the vector. That history vector will will store the cells intravasate in each time. We define that vector as 12 hours. So we define one vector who the length you're able to store 12 hours, and storage all the intravasation cells and each phenotype time step. After storing them, we rotate that vector for the next time step, and check if that old old position of that vector who represent the 12 hours ago, if have some cells for extravasating. If have some cells for extravasate, we multiply by this response factor. This response factor is just giving us the idea for one cells who's intravasating for one EPC, what will be the response factor according to that cells for generate T effector T cells. And according to that response factor and the numbers of the cells 12 hours ago, we are creating the effector T cell randomly in the domain according to that vector, to that counting from the number of the effector T cell extravasation. And by end of the writing that function, we will call that function main.cpp. So just explain here how we selecting randomly that position. We basically starting here by selecting the range of the domain, the X range, Y and Z ranges, and using the uniform random for each of this range for defining the position of the new cells and using the function assign position. So in the main.cpp, we basically just call this function lymph node update. In this place, it's able for adding on functions. And this is the majority of the project. Have some another changes. And when you export, you can see is basically I create some kind of the variable, global variables, where I store the quantity of the intravasating cells, as you notice here, and that vector for storage all these 12 hours of the simulation for storing the quantity of the cells and visiting that story of the vector each time you do the lymph node update. So this is all I have here to present. Thank you.